All right, so let's get going on talking about stacks. Now, as I mentioned in the introduction, the stack is a conceptual or abstract data type. So what it does is it dictates the operations we can perform on a set of data, but it doesn't tell us how the data should be stored. A stack says, I don't care how the data is organized, but these are the operations you're allowed to do on the data. And so basically, a stack can be backed by any data structure. Now, it doesn't make sense for it to be backed by some data structures, but you could back a stack with any data structure you wanted. So let's talk about the operations we can do on a stack. Well, one feature of stacks is that the last object, the last item, element that you add to a stack is always the first item that you can remove from the stack. And so that's known as LIFO, last in, first out. So that means there's no random access. We can't do what we can do with an array and just say, hey, give me the element at position 5, because you're only ever allowed to remove the last item that you added to the stack. And because of that, as we'll see in the upcoming slides, the stack has the concept of a top. So we talk about the top of the stack. The item at the top of the stack is the only item that we're allowed to access. It's the only one that we're allowed to look at, and it's the only one that we're allowed to remove. And so imagine a deck of cards or a stack of papers. So if you have a stack of paper, if you want to get to the paper that's 10 pages down on the stack, you have to remove the 9 pages that are on top of it first. Or if you have a deck of cards and you want to get down to the 10th card in the deck, you have to remove the first 9 cards before that 10th card is going to be at the top of the stack of cards. So it's last in, first out. If we add a paper to the stack, then next time we need a paper, we're going to be taking the paper that we last added. Now, we've seen one use for a stack, and that's the call stack. When we looked at recursion, I talked about pushing method calls onto the call stack and removing them from the call stack. And in that case, the last method that we called was always the first one that got taken off the call stack. I mean, if method foo called method bar, it wouldn't make sense for method foo to return before method bar does, because foo has to wait until bar finishes executing. So a stack is the perfect data structure to use for the call stack. Now we can perform 3 operations on a stack. We can add an item to the top of the stack. That's known as a push operation. We can remove the top item on the stack, and that's known as the pop operation. And we're allowed to peek at what's at the top of the stack. Now when we do a peek, we can get the first item on the stack, but we don't actually remove it. And so a pop removes the item from the top of the stack, but a peek just allows us to access the item, but we leave it on the stack. Now, I said that a stack can be backed by any data structure. It can be backed by an array, but if you think about it, a linked list is the perfect data structure for a stack, because in a linked list, we always want to be working with the item at the front of the list if it's a singly linked list. And so we add items to the front of the list and we remove items from the front of the list. And by doing that, it means that the last item we added will always be the first item that we remove. And so a linked list is a perfect data structure to back the stack. And in that case, a push would be an add to front method, a pop would be a remove from front method, and a peek would just give us the head item without removing it from the list. So it's pretty common to have a stack that's backed by a linked list. But as I said, you could also back a stack with an array. So let's take a look at the stack. So here's an empty stack. There's nothing on it. So the top would be null if we were dealing with a linked list. And then let's say we push Jane. Well, Jane will now go into the stack and she's the top item on the stack. So we have a top pointer or a top variable that's pointing to Jane. And then we're going to push John. So John is now at the top of the stack. And then we're going to push Mary. So Mary's now at the top of the stack. Now, if we did a pop at this point, Mary would be the pop value because Mary's at the top of the stack. She was the last item to be added to the stack. And so if we do a pop, the popped value will be Mary and the new top of the stack will be John. Now, if we do a peek, the peak value will be John, but you'll notice that John is still on the stack. So here's the state of our stack before doing the peak, and after the peak, John is still on the stack, but we've been able to access him. We've stored him off in some variable, so we can look at what the top item of the stack is. So those are the three operations that we can do on a stack: push, pop, and peek. And because of that, a stack has LIFO behavior. The last item pushed onto the stack will always be the item that's popped from the stack. So let's talk about time complexity. Well, this is going to depend on how you're backing the stack. What data structure are you using to implement the stack? Now, if we're using a linked list, the push, pop, and peek operations are going to be constant time, because when we looked at linked lists, we discussed that because we're always operating in the case of a singly linked list, which is all you'd need for a stack. For the case of a singly linked list, to add an item to the front of the list is constant time. To remove an item from the front of the list is constant time. And if we wanted to get the head of the list, which would be a peek, that's constant time. Now, if we were to use an array, then push could be linear time, because if the array is full, we'd have to resize the array, and we'd have to copy all the existing elements on the stack over to the new array. So as I said, the time complexity of the operations is going to depend on how you're implementing the stack. What data structure are you using to back the stack? Now, if you know the maximum number of items that will ever be on the stack, then an array could be a good choice, because you could declare an array that's large enough to hold the maximum number of items, and the array would never have to be resized. If memory's tight, an array might be a good choice, because with an array, you don't have the overhead of having to have a next field. But if memory isn't tight, and if you don't know what the maximum number of items is going to be, then linked list is ideal. And even if memory is tight, a linked list would be ideal if you don't expect to be adding a whole ton of items. I mean, a linked list really does lend itself well to the behavioral restrictions that a stack has. So now that we understand what a stack is and we understand the operations we can do on a stack, let's implement a simple stack. I'll see you in the next video.